then if you take a square, okay, so this means that the cosinus 2 theta is 0 and is 1. So it's very simple. 1 is here. So that means that what is this? This is therefore this is the other possibility is of course here minus. Okay. And similarly that's for the root minus I. So okay, just simple exercise to show that this is what is. So please, so if you know the solution, it's very easy. Just take a square, then you get the correct answer. Okay. So in this way, that there are many things. Even for the Euler, later is a mistake for the calculation of complex numbers. So he wrote that in his very famous book on algebra, square root of minus 2 and square root of minus 3 is but today's notation, if you be careful, this is 2i and this is. So correct answer is minus 6. So for a long time, people really puzzled about the complex numbers. And actually, it was in the 19th century, in the past, the many mathematicians realized that the importance of complex numbers. So before, it is, in a sense, it's a really mysterious number, and sometimes quite useful, but sometimes it's just misleading result. Okay. And then, yeah, history is rather complicated. And after the cubic equation and the quadratic equation are solved, the many mathematicians really tried to solve the fifth degree equations a long time. And it's not so easy. And on the other hand, gradually, mathematicians realized that nth degree equation may have n solutions. And first mathematician explained that nth degree equation has n solutions. Seems the French mathematician Zero. So he claims that nth degree equation has n solutions. Okay, so if you have then it has n solutions. But in each way, he didn't say that any solution, all solutions are real or complex numbers. He might think that there will be new numbers, and that goes further. And it's not clear for me that who was the first person who really proved that. The n-stable equation has n solutions. And usually, it is said that Gauss was the first person who proved that. But before Gauss, Euler and Laplace and D'Alembert really tried to solve it. And from modern viewpoint, their proof is, in some sense, quite correct. But of course, they lack that some very critical notation or notions, so that maybe in that sense it's incomplete. But it's a quite interesting history to study. But by the way, I'm very curious why that Asian countries like China and Japan and Korea, they never found the complex numbers. It seems quite interesting questions. Because even for the Europe, there is no reason that why they found that complex numbers. So maybe you can write a long papers about that. The one probable point is, especially in the Chinese mathematicians, they can solve any equation using this Chinese method. And so that they don't think about the number of solutions, and even that they wanted to have only the positive solutions. And in Japan, that later, so in the 17th century, Seki Takakazu, he really considered several equations, and he realized that many equations has at most n solutions. And he classified that equations according to the number of the solutions. Of course, he only considered real solutions. And then he never thought that any equation should have n solutions. Instead, what he did is he tried to change the coefficient of the equation so that the equation has n solutions. So he did completely different ways. So I don't understand. I don't know how that he didn't. Why he did not think about the possibility of new numbers.
That can be justified.
Pardon me?
Complex numbers is born by wild imagination, but maybe that's just what Eastern cultures lacks.
I think the Eastern culture also has a lot of imagination, but the imagination are completely different directions.
I think maybe because in China and in Japan, the people always to think about the concrete problem,
That's
to have a concrete
Yeah.
solution. So for that kind of problems, you never meet the complex numbers.
Yes.
It's not necessary to think about that kind of things.
Yeah, true.
Because the problem is come from the practical life.
Yeah.
So they quite few to think about, to study the features of the function.
Yes.
That's differences.
Mm-hmm. Yeah, of course we like the notion of functions. No? Yeah, but nevertheless, it's not so easy to answer this problem. Okay, so what shall we do? Continue or stop here a little bit? That's the best way. Because next I really want to go to the sort of the fundamental theorem of algebra. That means that L-stable equation with complex coefficient has always n solutions in complex numbers. And the history of that. And,
We might have a short break.
Sorry?
We might have a short break.
Yes, maybe
Maybe
it's
5
better
minutes.
than a short break.
5 minutes or so.
Okay.
Okay.
Well, any other questions? Maybe too fast or too slow?
Well, this is perfect.
Yeah. not you.
Or maybe
You are not a student. Yeah. GX. And what Euler tried is express this rational function as a sort of the partial sum of the fraction. So use some polynomial plus something like so it's complicated, but somehow in this form. And this means that this means you need to really express this polynomial as the linear polynomials. So this means that fx equals 0 has n solutions or n roots. And once you know that, then that primitive integral of x minus ck n dx is very simple. If n is 1, this is log. Otherwise, minus 1 and then what is the constant? n minus 1. Yeah, then that after that, Euler and Bernoulli has a big discussion about this log because CK is in general complex numbers. So what is the logarithm of the complex numbers? And that's, for example, the simplest case is what is the logarithm of log minus 1 or log I? They had a big discussion about it because I squared is minus 1. And so if you use property of logarithm, should be log minus 1. And on the other hand, minus 1 square is 1, so 2 times log